My name is Vivek Seshadri. I'm actually a PhD student with Professor Onur Mutlu, and as you all know, he's out of town. And so I'm going to be talking today about this topic called in-memory processing, which is actually my own research area itself. So cool. So when I say in-memory processing, what comes to people's mind? Okay. So he said offload some of the tasks from the processor to memory. Does anyone else have any other notion of in-memory processing? Yeah.
Like doing sort of memory-to-memory instructions without having to go through the processor?
That's a bit more specific. I mean, doing memory-to-memory instructions without going to the process. Something like DMA. Yeah. Anything else? Cool. So we had a very general answer, and we also had a very specific answer, which is also part of this talk. So there you go. Okay. So we have two goals for this lecture, okay, as I have listed in the slide. So the first goal is to understand DRAM technology, which is the predominant substrate used for building main memory these days, right? So we'll look at how DRAM is built, how it operates, and also we'll look at some trade-offs that are involved in DRAM design. And in the second part of the lecture, which is actually more related to the title, we will look at whether we can use DRAM to do more than just store data, right? And more often than not, when a researcher asks such a question, the answer is yes. And we'll look at two specific examples of how we can use DRAM to do more than just store data. So one is in DRAM copying, which is something like what you suggested, right? Memory-to-memory operations completely within memory. And the second one is something out of the ordinary, in DRAM bitwise operations. So we will look at how we can use DRAM as it's built today to do bitwise operations, specifically bitwise and bitwise OR operations. Okay, so these are the two goals. So at the end of the lecture, if you guys can explain how DRAM operates and talk a little bit about those two ideas, I'll be happy. So how many of you have seen this? Cool. So I actually brought a DRAM module with me. So I take this with me to all my DRAM lectures, right? So this is basically a DRAM module that you can plug into your systems today and get more RAM. So this is actually a 2 GB RAM. People have like 8 GB modules these days. So the goal for the first part of the lecture is to understand how each of these DRAM chips are built, right? So there are 8 chips in that module, and we'll understand how each chip is built. Okay. So before we get into the design of the DRAM chip, what do you think are some of the goals for DRAM manufacturers? So if I am a DRAM manufacturer and I want to build DRAM chips, what would my goals be? Cheap. Density. So you can capacity. Low energy consumption. Fast, right? I mean, that's probably the first thing that comes to my mind, but yeah, fast. Anything else? Reliability, that's a good one. Anything else? Okay, so we want fast, cheap, reliable, high density memory, right? So I listed a few. I mean, I think I have some things here that are not there, and there are things that you said that are not there here. Like reliability was mentioned. I think I don't have reliability here. That's a good thing to add to this list, right? So cost, latency, you want whatever request that is sent to DRAM to be returned really fast. You want high bandwidth, right? There are applications that stream through a lot of data, and it'll be good to have a lot of bandwidth from DRAM. Parallelism. So why do you think parallelism is a factor? So parallelism in general improves throughput. Specifically in today's context, why would parallelism be important?
In multi-core systems, you might have two processors trying to access memory at the same time.
Absolutely, right. So in today's systems, we have not just one core that is accessing memory. We have many cores and possibly other agents as well. We have GPUs on chip these days. If you take your mobile processor, there are many more agents that are accessing DRAM, right? So you want DRAM to be able to serve all these requests kind of simultaneously. So you're expecting high parallelism, and one of you mentioned energy as well. I've listed energy and power separately here because they are actually two different things. You can actually increase the power consumption of DRAM, but reduce overall energy if you're improving performance. We will see an example of that in today's lecture, right? Anyway, so like I mentioned, our goal in the first part of the lecture is to understand how the DRAM chip is built. And this is basically a picture from this company called Chipworks, which essentially dissect DRAM dies and then come up with all these cool pictures about how DRAM is built. So if you look at more closely at this picture, you can see like 8 components. Right? Can everyone see like 8 boxes there within the DRAM chip? Anyone not seeing 8 boxes? Cool. So each one of these boxes is what is called a DRAM bank, right? And so essentially the chip is 8 banks put together with some I/O logic. So our goal really is to understand how a DRAM bank is built, right? And a friend of mine recently put, DRAM is like a fractal. You keep zooming into DRAM, you see, hierarchically more and more structures going underneath and underneath, right? So if you actually zoom into a bank, you'll see a huge hierarchy, right? At the bottom of the hierarchy is what you have these, right? Capacitors. So I hope all of you are familiar with capacitors, right? So DRAM technology is predominantly built using capacitors, and what is essentially exploited here is the capacitor can be in 2 states, right? The fully charged state and the empty state. And we are going to use these extreme states to store 1 bit of information. Right? But what is the problem when reading data out of a capacitor? Any thoughts? Destruction of state. What else?
Leakage.
Leakage, that's a good one. Leakage in some sense destroys state.
Right.
Yeah.
But as well, that you have to refresh even when you don't read.
Mm-hmm.
Title.
Yep. Good one. So someone mentioned capacity. So if I wanted a high capacity from my DRAM chip, what would I do to these capacitors? Make them smaller, right? So when you make them smaller, what happens? The charge capacity reduces, right? So essentially, my goal is to build really high-density DRAM, and if that is my goal, I would make these capacitors as small as possible. But as I make them smaller, the amount of charge that is going to be there in these capacitors is also low. Right? So essentially, we have these 2 problems. One is these capacitors are small, so they cannot drive your memory channel, for example, all by themselves. So you need some mechanism to take this state and convert it to some stable state, right? And the second problem is what he mentioned, like reading destroys state, right? So let's say my capacitor was fully charged and I tried to sense the data. It's likely that the charge is going to flow out and it's going to change the state, and I need a mechanism to restore the state after I read, right? And a kind of a complementary problem is what you mentioned is the capacitors are leaky, right? So if the charge is leaking over time, then even if I don't read the data from the capacitor, I need to somehow refresh the data every once in a while. So we won't look at that problem, but let's look at what DRAM manufacturers do today to address these 2 problems. Right? So they use this component called a sense amplifier, right, which is what I've shown in this slide. It's essentially 2 inverters connected in the manner shown in the slide. Right, and as you can see, there are 2 terminals to the sense amplifier at the top terminal and the bottom terminal. And the sense amplifier also has a signal called enable, which determines whether the 2 NOT gates are actually in operation or not. So in the enabled state, the sense amplifier has 2 stable states. Again, as I have shown in this slide. Right? On the left, we have the top terminal at VDD, or a logical 1, and the bottom terminal at 0. On the right stable state, we have the top terminal at 0 and the bottom terminal at VDD. Right? So it's clear why these are stable, right? Because each NOT gate is going to take a value and feed the inverted value to the other terminal, and the other NOT gate is going to do the exact opposite. Right? So again, so we have 2 logical states here, which means this the sense amplifier can actually be used to represent a single bit of information. Right? So let's quickly look at how the sense amplifier operates, right, from a disabled state. So let's say initially my top terminal was at some voltage level Vt, and the bottom terminal was at a voltage level Vb, and the sense amplifier was initially disabled. And let's, for this example, consider Vt is greater than Vb. Right? So what happens if I enable the sense amplifier in this state? The sense amplifier is going to take the top to VDD and the bottom to 0. So I'm not going to go into the details of how the sense amplifier actually does that, but it has to go to one of the two stable states, and this is the stable state that it goes to. Right? And if VB was less than VT, then the sense amplifier would go to the other stable state. Right? And what we're essentially going to do is we're going to convert the state of the capacitor, either the empty state or the fully charged state, to one of the two stable states of the sense amplifier. Right? And since the sense amplifier is stable, it's possible for us to read or write data into the sense amplifier. So this is the structure that we are going to use to convert the state of the capacitor to a stable state of the sense amplifier. It's as shown, we have the capacitor on the top left and the sense amplifier, and there's a switch that connects the capacitor and the sense amplifier. Right? And as you can see, the sense amplifier is initially disabled, and both the top and the bottom are set at half VDD, midway between the maximum voltage and the minimum voltage of 0. Right? So in this state, if I want to read the data from the cell, I close the switch, connecting the capacitor to the sense amplifier. So what do you think will happen in this state? The cell is fully charged. What's going to happen? Okay. So the charge. So what is the voltage level on the capacitor right now? It's fully charged. So at what voltage level is it? VDD. So the capacitor is at a voltage level of VDD. The top terminal of the sense amplifier is at a voltage level of half VDD, and charge flows from a higher voltage level to a lower voltage level. Right? So the charge in this case is going to flow from the cell to the top terminal of the sense amplifier, increasing the voltage level on the top terminal to a half VDD. Right? And in this state, if we enable the sense amplifier, what's going to happen is, based on the operation that I described before, the sense amplifier is going to go to a stable state where the top terminal is at VDD and the bottom terminal is at 0. Right? And since the capacitor is still connected to the sense amplifier, the capacitor is going to get fully charged. Right? So in some sense, this particular structure solves both the problems with the capacitor. Right? I mean, initially the capacitor had very little charge, and we have found a way of converting that very little charge to a stable state of a sense amplifier. And this mechanism also restores the data on the capacitor after reading. Right? So we don't have to worry about the cell's state getting destroyed by the read operation. Right? So what should we do? Should we build just one sense amplifier for each cell? Is that a good idea? Why not?
It's too much circuitry.
It's too much circuitry.
Yeah, like it'll take up too much space.
It'll take up too much space. Right? Absolutely. So if I were to build one sense amplifier for each cell, then why have the cell in the first place? Right? So in fact, if you remove the cell and just have the sense amplifiers, that's SRAM today. That's how we build processor caches today. Right? So clearly, having one sense amplifier for each cell is not a great idea because it's going to cost. What else do you think will add to cost in this particular structure? Like, we just don't have the capacitor and the sense amplifier. We have something else there. Come again? Access transistor. So basically, we have a switch, right? So we need some logic to say whether that switch is closed or open, right? So what controls that logic? Or in sense, what is that logic a function of?
The address.
The address. right? So I want to access some piece of data, and I provide an address to DRAM, and it really depends on whether this address corresponds to this cell or not. So again, should we have each address access one cell? Why not?
Because the addresses typically are corresponding to more than one bit.
OK, so what would be a good number?
Say 8.
8 bits?
If we want an individual bit or individual byte.
Individual byte. OK, so if you want an individual byte, we would want each address to correspond to 8 bits. So should we have that logic for every 8 bits? Why not? Expensive, right? So even if you have, let's say, one cache line, right, which is 512 bits, that the logic that we need to build to control that one access transistor is expensive. So we want to amortize the cost of controlling that logic across a wide number of cells, right? And similarly, we also want to take the sense amplifier and amortize the cost of the sense amplifier across a large number of cells, right? Which is why DRAM manufacturers do this, right? So here I have shown a 4x4 picture, but in reality, it's something like a 512x512 or a 1024x1024, right? So what you see is the green boxes at the bottom are the sense amplifiers themselves, and the blue circles are the DRAM cells. And as you can see, each sense amplifier is shared by a large number of cells, and similarly, each row of cells share the same line that controls the access transistor. So that line is called the word line. So essentially, if you raise the word line for a particular row, you are in some sense accessing all the cells in that particular row, right? Essentially firing all the sense amplifiers simultaneously, right? So in fact, it turns out this is not sufficient. So they actually build a much wider structure, which is what we call a DRAM subarray. So a DRAM subarray is essentially multiple of these tiles put together with a single row decoder on the left, right? So essentially, if you want to access some piece of data, you figure out which row the data is present in, and in some sense fire all the cells in that particular row simultaneously, right? And they do more, right? So remember, I mentioned the sense amplifier as 2 terminals, right? The top terminal and the bottom terminal. Right? In the example that the example operation that I showed, I just showed one cell connected to the top terminal. But in some sense, if you look at it, the sense amplifier is very symmetric, right? I mean, there is no difference between the top and the bottom, unless you fix one of them to a cell, right? So why not connect the bottom parts also to a few DRAM cells, right? So that's what they do, right? So they connect the top part of the sense amplifier to a bunch of cells, and the bottom part of the terminal also to a bunch of cells. So essentially, you have this wide structure, which is heavily cost amortized, right? So, and our DRAM bank, which is what we want to know more about, is built this way. Right? You take a bunch of subarrays, and then you stack them on the chip, right? And each bank has something called a bank I/O logic, which essentially reads the data from the array of sense amplifiers and sends them out, right? So just to give some numbers here, the subarray is around 8 kilobits wide, which means each row in DRAM contains 8 kilobits. But if you look at the bank I/O logic here, which essentially reads data from the sense amplifiers and sends the data out, it's only 64 bits. Why do you think that would be the case? Why can't the width of the bank I/O also be 8 kilobits in some sense?
It's a lot of wires. There's a lot of pins to have 8 kilobits of bandwidth.
OK, so you're saying it'd be a lot of pins going down.
Yeah.
OK.
Also, isn't it only sending out one cache block at a time, which isn't necessarily the whole row size?
OK, so it's just sending one cache block at a time, which is not the entire row. So in some sense, so what you point out is a cost factor going out, and you specified a need factor going out. So you said it'll be extremely costly to have, 8 kilo pins, and you are saying you wouldn't need 8 kilobits of data anyway. Do you think there'll be some factor going in like the connection between the anyone? So what do you think will take to have 8,192 lines going from here all the way to the top? Do you think that will be feasible? You're all electrical engineers. Okay, the answer is no. It's not possible. Right? It's not possible to have 8,000 lines going from here, spanning the entire width of the chip, or the width of the bank in this case. Right? It's because these wires have to be thicker because they are spanning a longer distance. So for our consistency or integrity of the data, you have to have them thicker. And once you make them thicker, it's not possible to have 8,000 lines. Right? The chip is not wide enough. So essentially, this is what they do. Right? So they have each address is split into two parts. Right? So you want to access a cache line, you first specify which row the cache line belongs to, and then within that row you have a column address. So you split the address into two parts. One is the row address, and the other part of the address is the column address. Right? So if you dive into how exactly, okay, so this is before we go into the DRAM operation. So this is the DRAM chip that I showed before, and essentially what you have is the banks filling the chip. Right? So in this case, we have 8 banks, and all these 8 banks essentially share an internal bus, which connects the bank I/O logic of each bank to the memory channel that is outside of the chip. Right? So here is a small example of how DRAM operates. Right? So let's say we wanted to access the black cache line from that white row on top. Like I mentioned before, the first thing we do is we identify the row address of that cache line. Right? And what the memory controller, which is actually controlling the DRAM, will do is issue a command called activate to that particular row address. And what this does is it raises the word line of the corresponding row, and it triggers the operation that I described. Right? Remember the single cell to the sense amplifier operation that I described. It triggers that operation across that entire row. And what that does is it essentially copies the data from that row of DRAM cells to the corresponding array of sense amplifiers. Right? Then the next step is to access the cache line that we want. Like I said, again, the memory controller identifies which column that particular cache line is, and then feeds issues a read or a write command to that particular column. And what this does is it sends the column address to the bank I/O logic, and the bank I/O logic reads the corresponding column of data and sends it out of the bank through the memory channel to the memory controller. And finally, when we are done reading the data, if you want to access, let's say, a different row from the same bank, we have to take the bank back to the original state. Right? So that's done by issuing a command called precharge. And what this is essentially clears the sense amplifier and takes it back to the half VDD state, which is also called the precharge state. Okay, so these are in some sense the 3 commands that you need to know about DRAM access. Right? An activate to the row, which essentially copies the data from the row DRAM cells to the sense amplifiers, and then a read or a write command, which actually does the data transfer either from the DRAM chip to the memory controller, or in case of a write, from the memory controller to the DRAM chip, and a precharge, which essentially clears the row buffer and prepares the bank for the next access. Okay. So this lecture is getting over much faster than I thought. So how long are your typical lectures?
2 hours.
Full 2 hours?
Or more.
Or more?
Or
He
more.
sometimes goes over.
How many slides are there?
Like 80.
90,
Like
80.
80.
80, 90?
Yeah.
Do you guys like it? Huh?
Yes.
Is it recorded? I mean, what they're saying as well on YouTube. So you better hope Onur is not going back and seeing all those lectures. Not this one, maybe. He probably does not have enough time to go over this lecture, so you're probably safe. So till now, what we have seen is, we have seen how DRAM is built today. I mean, there is very little more to what I described here. I mean, there is obviously questions about yield, more details on how the bank I/O logic works. So there are a little bit more detail to how DRAM operates, but it's as simple as what I described. And I was actually surprised that initially we used to have an abstraction for a DRAM bank, which is you read a row of data, and the pre-charge command actually writes back the data to the DRAM cells. So it's nothing of the sort, right? So it was in some sense very liberating to know how DRAM operation was so simple, right? So we looked at how DRAM is built. We looked at how it operates. We have not looked at any trade-offs. So let's just look at some trade-offs before we jump into the second part of the lecture, right? So these are, in some sense, some of the design goals that I specified, in the beginning of this lecture: right? Cost, latency, bandwidth, parallelism, power, energy. So, like I also mentioned in the beginning of this talk, it will be extremely great if I can build cheap, fast, high bandwidth, highly parallel, low power, low energy consuming DRAM and reliable DRAM. But do you think that's possible? What would someone do if it was possible to build a different DRAM architecture, which is faster, more bandwidth, more parallel?
It would be unique and the cost would be naturally high.
If it was also cheap, I would be building that architecture. So clearly, I have maxed out, right? So if I want to do something, if I wanted to build a faster DRAM, it's probably likely going to be costlier as well, or I'm going to trade off with some other parameter, right? So let's set aside cost for now. What do you think affects the latency of DRAM? I mean, I described the design so far.
Capacity.
Capacity. So you're saying if I built smaller DRAM, I would get faster DRAM.
If you have less capacitors to charge and stuff, then your clock cycle could be faster.
If I add. One second. So basically, but here is the thing, right? So when you say lower capacity, there are many ways to achieve lower capacity, right? So I mean, we have seen a hierarchy in the DRAM chip, right? There are banks, there are subarrays within a bank. So if I build, let's say, a chip with fewer banks, do you think they'll be faster? Probably. Not much. You had some answer.
I was going to say, the charging of the capacitor is probably going to take some time, and the logic that people are going to point out the logic that it takes to decode the address.
Mm-hmm. So you are going to say the logic that decodes the address. Okay. You have an answer?
I was going to say bitline length.
Bitline length? Have you read some paper?
Yeah.
Which one?
The tier latency
Okay,
one.
so you know the answer already. Okay. This is kind of a really wide classroom, right? How does that feel? I was sitting in a job talk here one day, and this was a faculty candidate talk, and someone from there asked a question, and the faculty candidate walked here, and then he was answering the question, and then he was standing here and looking at people, right? And there was one guy raising his hands vehemently there, trying to ask a question, right? So it's very weird that we have a very wide structure for a classroom. It's better if the aspect ratio is longer than wider. Anyway, he's right. I mean, he has read the tiered latency DRAM paper, which essentially describes this trade-off, right? The number of rows you have within each subarray, right? That in some sense dictates how long your bit line is going to be, right? And the reason why that is the main factor is because the bottleneck for DRAM latency today is how fast can the sense amplifier drive a specific voltage level on the bit line, right? So In some sense, we saw that the sense amplifier was driving the bit line to VDD, or even driving the bit line to half VDD in case of the pre-charge operation, right? So how fast can we push the bit line to a specific voltage? That's the bottleneck for latency in DRAM today, and that is essentially determined by how long the bit line itself is, right? And if you have fewer rows within connected to each bit line, then we'll have a higher latency. But what is the downside of having fewer rows per subarray? For a given capacity, let's say I was building a 2 gigabit DRAM chip, and I decided, OK, I will have fewer rows within each subarray.
Then you have more columns, you have bigger row buffer.
Let's say everything else is fixed. OK, so the row buffer size is fixed. The
You need a bigger decoder to access different rows.
you need a bigger decoder to access different rows. OK. Why is that the case?
For a fixed capacity, you would have to choose between the rows if you have to maintain capacity.
Mm-hmm. So the number of rows hasn't changed, right? So it's in some sense the same number of address bits that I'm decoding, right, at the end of the day.
Each subarray would have some sense amplification at the end of it, so that would increase the size.
Can you be more? You're there, but can you make it more clear?
I just mean to say that each subarray would have like sense amplification for the rows selected. So those combined for all subarrays would increase the.
Absolutely, right. So essentially, we have fixed the capacity, right, and we have reduced the number of rows for each subarray, which means we are in some sense increasing the number of subarrays, right? Now we need more subarrays. The problem is each subarray comes with a fixed cost. And what is the fixed cost? The sense amplifiers, right? And that was something that we wanted to reduce in the beginning, and that fixed cost is going to increase the overall cost. Now I have to build a bigger chip to get the same capacity, right? If I decided to go with fewer rows per subarray. Speaking of which, there are actually DRAM manufacturers who build chips with smaller rows per subarray than this is like commodity DRAM. So if you search for reduced latency DRAM, there is a market for such DRAM chips, right, which have much lower latency than what we have today. Okay. Bandwidth. What do you think affects bandwidth? Okay, let me ask a different question. Why do you think I have 8 chips on the DIMM? Why not just have one?
With this, you can parallelly access the 8 banks and serialize the output from these banks.
Okay, so let me make one thing clear. Okay, this was the first misconception that I had. So I looked at this DIMM and I thought each thing here was a bank of DRAM, but that's not the case. Each thing here is a chip, and each one has 8 banks within itself. Okay.
So each one is a rank.
Okay, you're getting into terminology which I don't want to get into, but it's okay. So rank. So what is your next point?
No, I'm just wondering, is there a different rank?
Okay, so now because you introduced the terminology, let me talk about it anyway. So this is a DIMM, right? But in this DIMM, if you see, there are 8 chips on this side. There are 8 chips on the other side as well, right? So in total, this particular DIMM has 16 chips, right? So this is what is called a dual inline memory module, right? Which means I can either access these 8 chips at a time, or I can access these 8 chips at a time. But I cannot access all 16 of them simultaneously. Okay, that's what is called a dual inline memory module. I think in previous days they used to have single inline memory module, which means they had only 8 chips in the module. And like he points out, these 8 chips form what is called a rank. Okay, and the 8 chips on the other side form a different rank. So essentially, this particular module has 2 ranks of 8 chips each. So what does the word rank mean? Have you guys heard of rank of soldiers? So what do they do?
It's a line of soldiers.
So they have a line of soldiers, and
another line of soldiers behind them.
what do you think is the purpose of having, like groups of soldiers like this, and not have one soldier in each group?
Manage them in groups.
You can manage them in groups, right? So if I, as a commander, I can just say, this rank, go and do this, right? Instead of saying each soldier, hey soldier, you go do this. Hey soldier, you go do the same thing, right? So I can, in some sense, give a single command to an entire rank, and all the soldiers within the rank can obey that command, right? It's the same thing, right? We have 8 chips in a rank. In some sense, I can give a single command to all the 8 chips simultaneously. That's the purpose of having a rank. But why would I have a rank of 8 chips and not have? It seems like controlling each chip individually can be better, right? I can say, oh, chip 1, give me this piece of data. Chip 2, give me this other piece of data. And that will give me more parallelism, right? I can access different pieces of data from each chip. I get more parallelism. But why would I combine 8 chips together and say, okay, I'm going to give the same set of commands to these 8 chips all the time?
To reduce pin count of your command bus.
To reduce the pin count of the command bus. That's a good one. So if I had to give a separate command to each chip every time, it means I would need 8 times the command bus bandwidth. Right? I need 8 times more pins for my command, and what? Just the command? And the address bus. Right? I need 8 times more pins for both the command and the address bus. Okay, 1 point. What is the benefit of having 8 chips? That's like avoiding a cost, right? Is there any benefit of having 8 chips operating together?
You can get 8 bits of data from each one of them and make 64.
Absolutely, right? So in some sense, the primary reason for putting more chips on a single rank is bandwidth, right? You want to get more bandwidth out of the entire system, right? So if you actually go to embedded processors, they have fewer chips per rank, right? Because there you want to reduce. The other problem with having 8 chips is each time you give a command, you're firing 8 chips, which is more power, right? More energy. And in embedded process, you want to reduce that. So if you look at your mobile processors, you probably have 4 chips in a rank, or even fewer chips in a rank.
Why not just get 64 bits from one chip instead of doing 8 from each?
Brilliant question. Who wants to answer the question?
It's cheaper to have 8 bits in single chip.
Cheaper.
Modularity, something like that.
What do you mean by modularity?
Like, I don't know, like if one thing gets messed up, then everything gets messed up.
No, not that. It's I mean, if you want to build 64 pins coming out, you have to get the data to send out 64 bits, right? So his suggestion was, instead of having 8 bits coming out of each chip, right, which is what I showed in one of the slides, I think, right? So I think in the previous slide. Here I showed, okay, each chip sends out, has a data width of 8 bits, right, which is typical today. I mean, there's no reason why you cannot have 16 bits or 32 bits, right? But let's look at what is the cost of increasing this number, right? If we increase this number, we get more bandwidth too, right? So let me go back to the slide. We were here. So if I want to send 16 bits of data per cycle, right, then I need to get that much amount of data in advance, right? Which means I have to increase the amount of data that I'm reading from the subarray at the bank I/O level, which means my bank I/O should be wider.
But since you already have at least that much data in your row buffer, isn't it not that much extra cost?
So there's a row buffer which has 8 kilobits of data. So my row buffer has more than enough data to send even, let's say, 512 bits, right? Absolutely. But there was another bottleneck at the bottom of the bank, which was the bank I/O logic, which I said in today's systems typically has 64 bits, right? Now it seems like even 64 bits is wide enough, right? I'm just sending 8 bits. Why would I fetch 64 bits in my bank I/O logic if my data width is only 8 bits?
You can send out the next bits in the next loop. It's sort of like a prefetch.
Sort of like a prefetch, because you can send out the next bit in the next cycle. So does anyone know why today's DRAM technology is called DDR, double data rate?
On each clock edge. On both the clock edges, it sends out data.
Okay, so you guys know about clocks, right? So a clock has both a positive edge and a negative edge. And DDR essentially means we're going to send out some piece of data in both edges, both the positive edge and the negative edge, right? Still, I have 64 bits of data fetched into my bank I/O logic, but I'm just sending 8 bits at a time, which means, and each half cycle 8 bits are sent out, which means I'm spending 4 cycles sending out the 64 bits of data that I got. What benefit does this give? Why do you think I would only send 8 bits per half cycle?
Reduce number of pins.
Reduce number of pins. What if I wanted to send 64 bits? Okay, I think a better question could be, what if let's say I have a 64-bit or an 8-bit wide bus, right? Instead of sending, or let's say I made that bus 64 bits wide, right? And if I wanted to send 64 bits in one clock cycle or one half cycle, what should happen internally within DRAM?
You should transfer ideally synchronously all the 64 bits, which is hard in terms of timing and alignment.
So you're getting there, but what is the problem? Okay.
The delay matching would be very hard, I believe.
Okay, so I think you're giving the answer speed, right? So which means if I have to send 64 bits at the same time, that means I have to build faster DRAM, right? And today with the technology that we have, it won't be possible for us to build faster DRAM, right? In fact, DRAM internally operates at 4 times lower frequency than the bus, right? So today you may have heard of DDR 1666, right? 1666 megahertz is, and again at four clock cycles is, if I'm sending data at each half cycle, it means the actual frequency is 1666 multiplied by 2, and DRAM internally operates at 833 megahertz for the technology, right? Which essentially allows it to, which is why we need that prefetch, right? If I'm sending out only 8 bits of data, I could have very well made my bank I/O also 8 bits. But I need to fetch 64 bits because that's when I can match the bandwidth of the external bus.
Which logic is it of which frequency you're talking about, the 800? Is that the bank I/O logic or what? What is the slow thing?
It's basically the internal DRAM cycle. So internally DRAM internally operates at cycles. Okay, sorry, I don't want to go to the picture now. But there's an internal clock for DRAM.
For firing it and bringing it down to the row buffer and all of that.
Exactly, right? So just before the data is sent out on the memory channel, there is a register where it stores the 64 bits that it's going to send out in the next 8 off cycles. Everything above that operates at 4 times lower frequency. Everything below that operates at bus frequency. Yeah.
So why not get 512 bits and then send out 64 over the next 8 cycles?
What's the problem? You tell me. Cost. Because now if I have to get 512 bits from the row buffer to the bank I/O logic, means I have to build 512 wires that span the entire chip. Cost. Okay. So in some sense, the the trade-offs are basically the data width of each chip, which we can increase at a cost, or the number of chips per DIMM. We can also increase the number of chips per DIMM. But again, like we have discussed, having more chips in each DIMM means you are spending more power for each axis. Right now, I'm finding more chips for each axis. Okay, this is the last thing that we'll discuss from this trade-off perspective: parallelism. And what do you think affects parallelism of DRAM today? Like, what factor would I increase if I wanted to increase the parallelism within DRAM? Banks. Number of banks within each chip. Okay. So in this particular picture, in the DRAM chip picture that I showed, we had 8 banks, which means I can sort of activate. I must potentially be able to activate 8 different rows within 8 of those banks, right? Which means I can parallelize 8 different requests simultaneously. So if I had more banks, clearly I would be able to parallelize more requests, assuming those requests go to different banks, right? But again, increasing the number of banks is what? More cost. Why?
It's physically more stuff.
Same reason, right? So yeah, you have each bank has a fixed cost, right? The bank I/O logic. There are some row decoders for each bank that you need. So each increasing number of banks, again increasing cost. So for a fixed capacity, if you want to have more banks within the chip, that's more cost, right? So in some sense, the chips that are built today are at some point in this trade-off spectrum that the DRAM manufacturers have decided, okay, this is the right point for the amount of speed that we can get from DRAM, right? So it's possible to make DRAM chips faster. It's possible to make DRAM chips provide you more parallelism if we are willing to spend that additional cost. Okay, so we're done with the first part of the lecture, and I understand you guys usually take a break between the 2 parts. So I have successfully extended that one slide for 20 minutes. So yeah, we can take a break right now, during which time if you guys have any questions, you can shoot. If you want to go grab some water, use the restroom. Can we start? Yeah. So so his question was, what is the difference between DDR2, DDR3, DDR4? Like what changes, right, between these generations? Right? If you think about it, DRAM is probably one of these technologies where you have the memory itself built by one company, Samsung, Micron, whatever, and the controller built by a completely different company, right? Because memory controllers today are on chip, right? Which means Intel is probably designing the memory controllers, and Samsung is manufacturing the DRAM modules, which means there needs to be a specification wherein Intel knows how many banks are going to be there within the within each module so that they can actually access the data, and on the other hand, Samsung also knows how many banks to build within each chip, right?
It's just setting a standard.
So it's basically that standard, right? And the goal, of course, is to enable higher capacity per module, maybe lower latency and higher bandwidth, higher parallelism. Right? So you come up with some specification. So as technology progresses, there may be a specification for 2 gigabit chips. There may be a specification for 16 gigabit chips, things like that. Okay. So now we'll jump into the second part of the lecture, which is essentially, like I said, related to the title of in-memory processing. And the question that we're asking is, can we use DRAM for more than just storage? Right? And like I said, we are going to look at 2 instances of mechanisms which can actually do that. Right? The first one is in DRAM copying. So we actually wrote a paper on this a couple of years ago. So the mechanism is called RowClone, and it's actually a mechanism to do bulk data copying completely within DRAM. Right? So okay, I'm going to skip this because this is our goal. Right? Our goal is to reduce unnecessary data movement on the memory channel that's connecting the processor and main memory. right? And what do we mean by unnecessary data movement will be clear in a minute. And we are looking at two operations, right? Bulk data copy and bulk initialization, right? Bulk data copy is you have a source location in physical memory and a destination location in physical memory, and you want to copy some region of data from the source to the destination, right? So it can be a page copy, right? Copy 4 kilobytes from this page to this page. Bulk data initialization, it's very similar. So you want to initialize a large region of data with some value. It can be your memset, right? So you allocated a huge data structure and you did a memset on the data structure. Set the values to 0, right? And there are many different instances where these operations are very useful, right? For example, if you just fork a process, you are likely triggering a lot of copy operations, right? So whenever one of the fork process updates a page, you're going to create a copy maybe, right? And many other instances where these two operations are triggered, right? So they're both important operations, and speeding them up is going to boost system performance, right? So let's look at what is the problem with existing approach for doing data copy, right? So let's say we want to copy data from the source here to the destination, right? What do you think is the best thing we can do today? Copy it to the memory controller and send it back. Is it possible today? Like so let's say you were to write a program on your laptop, what do you think will happen? It'll go all the way to the cache and then go back, right? So it's like you're here, I'm here, and I want to send you a piece of letter, and we send it all the way to the post office. The postman comes and delivers it to your house, right? That's exactly what happens, right? I want to copy the data from the source to destination. It's sent all the way to the cache, and in the cache, you actually do the copy, and at some point, you may write the data back to the destination, right? Very inefficient, right? First, it takes high latency, right? Because we are doing the copy like one cache line at a time, right? So it would be amazing if we can. Somewhere we spoke about need for reading a large amount of data, right? Maybe if I had that 8 kilobit bandwidth, I could have just read that all the 8 kilobits in one shot and written it back in one shot, right? So, but here we have to do it at a cache line granularity, which means it's high latency. It takes around a microsecond to copy 4 kilobits of data, right? It causes interference, right? Because let's say the other core wanted to access some other piece of data. Your bus is busy doing copying. So it causes interference to the other cores, right? And finally, it consumes high energy, right? The memory channel, because it connects two structures which are considerably separated, right? You need to spend a high energy to ensure signal integrity, right? So again, around 3 microjoules for the copy operation. Yeah.
Yeah, I have a question. How did you measure the energy, the free phone and 600? You do it by simulation?
It's modeling basically. So there is again a standard power model that is available, a tool that is available, where you can just feed in the set of commands that you issue, okay, and the tool will spit out how much energy this sequence of commands is likely to consume.
Okay, cool.
Yeah. So it's not a real measurement, right? So like at least the latency is believable, or trustworthy, because there are sequence of timing constraints, and you can actually estimate the latency to a very high accuracy. The energy is tricky. Right? It also depends on manufacturer, right? Different manufacturers may have different tricks to reduce the amount of energy that they consume, right? Anyway, so all three are bad, right? It's bad for performance, it's bad for energy. Can we do better, right? And our approach is essentially simple. Let's do the copy within DRAM, right? Sounds nice, because we won't have any of these 3 problems, right? But the question is, how do we do it? Okay. That's RowClone. Okay. Just by looking at this picture, can someone guess? Has anyone read that paper, RowClone paper? Please raise your hand. Those people are not allowed to answer. But almost everyone. You haven't read the paper. You have read the paper. You? No. Do you want to take a guess? How do you copy? So there's a source. Let's say I want to copy data from the top cell to the bottom cell. So first enable the switch for the one that you want to copy, and then enable the switch for the one that you want to copy into. Yeah. Okay, so that's absolutely right. That's what we're going to do. So let's say we want to copy data from the top cell to the bottom cell, right? We first enable the switch for the top cell and actually trigger the sense amplifier operation, right? So what this is going to do is it's going to take the sense amplifier to a stable state where it matches the data of the top cell, right? And it's also going to okay, so it should have refreshed the data on the top cell. So I don't know why I missed that animation. So the top cell has to be fully charged. I'll fix that when I provide the slides online. But now you look at the sense amplifier, it already contains, or it already represents the data of the top cell, right? In this state, if we connect the bottom cell to the sense amplifier, right? Normally what would have happened is the sense amplifier would have been, the top part would have been in half VDD, and the cell would have actually affected the data on the top terminal. But in this case, the sense amplifier is already in a stable state, right? Now the cell is definitely not strong enough to switch the state of the sense amplifier, right? So in this case, what's going to happen is the sense amplifier is also going to force the data into the bottom cell, right? So essentially, it results in a data copy. Yeah.
So can you do this with existing controllers just by issuing 2 activates, or do you need something else?
That's a great question. We haven't tried that, right? But what I understand is, I mean, we actually spoke to some. Okay, so before I answer the question, is the mechanism clear? Right? I mean, like you can convince yourself that for whatever initial state that you start off with for the 2 cells, this operation is going to result in a data copy from the 2 cells. And like he points out, the way you would implement this mechanism is just by issuing 2 activates, to the source row followed by the destination row, one after the other, and it should do the copy, right? Now the next natural question is, okay, if I just have to issue 2 activates to the source and the destination, can we do it today, right? That's a good question. You want to interrupt?
Yeah, this limits which cells you can copy into, right? Because they have all on the same sense amplifier line.
That's a very good point. So if I go to the next slide, okay, so I have benefits, okay, but that will come up, right? So clearly, a problem here, or I don't want to say problem, a limitation of the mechanism, as I have described so far, is you can only copy data from a source row to a destination row when they share a sense amplifier, right? I cannot, let's say, use this mechanism to copy data from one bank to another bank, right? That's a very right point.
Or even if there's an offset to a different column, let's say.
Yep. So the data has to be aligned, right? So it's going to copy the first bit of the first row, source row, to the first bit of the destination row. So even if the source and destination are within the same subarray, if they are not aligned, then again we cannot use this mechanism. Very valid point. So to answer your question, so first of all, we cannot do it on an Intel processor or an AMD processor because we don't have the ability to control the memory controller, right? Because Intel is issuing commands, and Intel is not going to issue one activate after another activate. So for us to test the mechanism, the only way we have is to use an FPGA. We have the infrastructure to test that. We spoke to some manufacturers, like Samsung, for example. And essentially what happens is all these chips that are built today, they have some internal mechanisms to prevent bad things from happening to the chip, right? So if you imagine, when I issue an activate, the DRAM chip expects the particular bank to be in the pre-charge state, right? But here we are saying, ignore that, right? If they are to the same subarray, if you issue the activate to the second row, it's actually going to result in a data copy. But what if that activate was to a different subarray within the same bank? The previous subarray was not pre-charged. Now if it is to a different subarray within the same bank, it's going to cause some problems, right? Now we don't know what problems it's going to cause, but it's going to cause some problems. So what DRAM chips do is they have some internal mechanisms to drop such violating commands. Apparently that's what Samsung does. when you issue things that you're not supposed to be issuing, they just drop it.
I think there's an internal FSM running once you get into that state.
Yes.
In order to get out of that state, you only have to go through a valid.
You have to go through a pre-charge. So you have to, in this particular case, you have to issue an intervening pre-charge. But we haven't tested that. So I think we could have tested that. We haven't tested that. Yeah. There are other issues as well. So there are, which I don't want to get into. Like for increasing yield, they may map a faulty row of one subarray to a row within some other subarray internally, right? Again, our mechanism wouldn't work in that case. So anyway, so let's quickly look at the benefits, right? Now, what I have achieved is a copy operation which can be 4 kilobytes across the entire module, right? So I can copy 4 kilobytes of data from one row to another by just issuing 2 back-to-back activate commands, which takes around 90 nanoseconds, right? So we have reduced the latency from 1046 nanoseconds to 90 nanoseconds, right? Close to 11x reduction in latency. And the energy goes from 3 microjoules to 40 nanojoules, right? Again, a significant reduction in energy, right? And almost no bandwidth consumption, except what? You have to issue the commands, that's fine. So when I say no bandwidth consumption, I'm saying there needs to be no data transferred between the processor and DRAM. But what can potentially cause a problem?
You still can't access the banks being used for the copy.
You cannot access the banks being used for the copy, that's absolutely right. But for the copy operation itself, so I'm saying there's no bandwidth consumed for the copy operation itself. But can something cause a problem which may require you to transfer data between the processor and the memory? Someone, you said something? You said something?
Cache.
You said cache, right? Of course. So what if I had, let's say, a dirty data from the source page in my processor cache? Possible, right? What should I do in that case?
You have to write into both the locations when you're exiting that block.
You have to write into both. So when you're evicting that block, you have to write into both locations.
Or you could copy first and then, or you could write back first and then copy.
That's a simple mechanism. Right? I can say, OK, before I start the copy operation, I'm going to check if the source page has any dirty block at all. If it has any dirty block, I'll just first flush them all to DRAM and then perform the copy. A very simple mechanism, right? If I wanted to implement your mechanism, how would I do that? So his mechanism was, if you have any dirty blocks on the source page, when you write it back, also write it back to the destination. That's a very high-level mechanism. How do you implement it?
You need some bookkeeping for sure to look at what the source and the destination.
OK. Yeah.
You could duplicate the cache block.
But that works, right? Just do the copy in cache. OK. So it turns out, I mean, we tested both mechanisms. Turns out the in-cache copy mechanism is much better. The reason is, if I can do the in-cache copy, I can do both the DRAM copy and the in-cache copy simultaneously. I don't have to wait for the in-cache copy to complete or the flushing to complete before I do the DRAM copying, right? Because if I'm doing the in-cache copy, it means I'm also creating the dirty block for the destination row. Now, it doesn't matter what the destination value is in DRAM, right?
What if it's not in cache?
If it's not in cache, then there's no problem, right?
The one you're copying. The destination is.
Yeah, OK. We are going to create an in-cache copy of the entire block. So it doesn't so you don't have to read the data in the first place, right? So the memory controller can essentially do the copy of the block. So it's essentially creating a new fake write back for a block that was not dirtied by the processor, right? OK. Very little changes to DRAM chip, right? I mean, clearly, the mechanism that you described also back-to-back activates, which is essentially what we can do with today's DRAM chip, right? And the only thing the DRAM chip has to ensure is that the back-to-back activates are going to the same subarray, right? Because if they're going to different subarrays now, that can cause a lot of problems. So that dropping logic that I suggested, we want it to be more selective, right? If the back-to-back activate is to the same subarray, then don't drop it. But if the second activate is to a different subarray, then drop it. That's the mechanism we need. And yeah. So some constraints with the mechanism, I think you pointed to one of them, like the location constraint. I mean, both the source and the destination have to be within the same subarray. They have to be aligned. There's a size constraint, like which is the entire row now gets copied. There is no, let me just copy this one cache line from this row to this one cache line to the other row, right? The entire row gets copied using this mechanism, right? But despite these limitations, we can accelerate, some existing primitives in today's applications, like copy on write, bulk zeroing. And if you read the paper, we also describe another mechanism which can copy data across banks, right? So how much time do we have? So time is 1:42. Okay. Anyway, so that's just the DRAM substrate part of it, right? Now clearly we have discussed some cache coherence issues, right? We have discussed some alignment issues, size issues. So we need support from the system stack to actually exploit this DRAM substrate, right? So that's this part. And again, if you can go through the paper for more details on these things, right? So in summary, we evaluated a bunch of different applications, which had varying levels of copying and initialization. And so the x-axis here is the applications that we evaluated, and the y-axis is basically comparison to a baseline, which is today's system, where you read the data into the processor caches, and then potentially write them back at a later point in time. Right. So this is like the performance improvement for each of these applications. You can see anywhere between 5% and 40%, and this is the energy reduction compared to the baseline. Again, we just evaluate memory energy, and anywhere between 15% and 60% reduction in energy. Right. So in summary, like a very efficient mechanism to do copying within DRAM itself. Yeah. So that completes the first part. For the second part, I just have 2 slides, right? So a slightly cooler mechanism, if I may say so. So let's say we want to do, so the goal is to do bitwise operations within DRAM, right? And this is more like, we did not start out with, okay, let's see how we can implement bitwise operations within DRAM, and then came up with this mechanism, right? We just thought what will happen in this case, and then it turns out we can do bitwise operations in DRAM. That's more the flow, right? So we have 3 cells here, right? A, B, C, all of them connected to the same bit line, right? And if I simultaneously connect all 3 cells to the bit line, what do you think will happen?
Wired OR. This resembles a wired OR.
This resembles a wired OR? The answer is wrong. You? You get a majority function, right? That's what you get. So essentially, we have 3 cells, right? And the bit line is at half. So if you have at least 2 cells which are fully charged, it means the effective voltage level on the 3 cells is going to be 2/3, right? But if you have at most 1 cell which is fully charged, the effective voltage level on the cells is going to be 1/3, which is less than half, right? So you get a majority function, right? So if at least 2 cells are fully charged, the bit line is going, the deviation on the bit line is going to be positive, right? It's going to be plus delta. On the other hand, if you had at most 1 cell that was fully charged, then the deviation on the bit line is going to be negative, right? Minus delta. So in this particular case, it's going to, the deviation is positive. The cell is going to get fully charged at the end of the operation, right? In some sense, the final state is this, right? This is the majority function, right? If you have 3 cells, it's AB plus BC plus AC. Interestingly, we can take this expression and rewrite the expression as this: C times A plus B plus not C times AB. What does this mean?
Depending on what value you set to C, you can control what is the remaining.
Absolutely, right? It means if I can control the initial value on the cell C, I can dictate what the final state is going to be. For example, if I know that the initial value of C is 1, then I know that the final state of the bit line is A or B. On the other hand, if I set the value of C to be 0, then I know the final state of the bit line is going to be A and B. Right? Now again, you can extend this operation to this operation is going to extend to a full row of sense amplifiers, right? Which means I can get a 8 kilobit wide SIMD AND or a SIMD OR operation using this mechanism, right? And what does this require? It requires the ability to activate 3 rows simultaneously and not just 1, right? So in some sense, if you think about it, a small change to the row decoding logic, but a huge boost in the functionality of DRAM, right? So essentially, we compared the throughput that we can get through this mechanism to what you may get through, let's say, Intel AVX, right? So today, on an Intel processor, the best you can do is use the SIMD instructions to perform bitwise AND or bitwise OR operations with a very high throughput, right? So essentially, we created a micro benchmark, and what the micro benchmark is going to do is it creates a vector of a specific size, or 2 vectors of a specific size, and performs a bitwise AND on those 2 vectors over and over again, and store the result in a 3rd vector, right? And the x-axis here shows the size of the vectors involved, right? And the y-axis is how much throughput we can get in terms of gigabytes per second of AND or OR operations, right? Now, let's say I run it on an Intel system. As the size increases, what do you expect to happen? I mean, is the question clear? So this is the size of the vector involved in the operation, right? And I'm repeatedly doing it on the same set of vectors, right? So if, let's say, the size was 8 kilobytes, it means I create one vector of size 8 kilobyte, another vector of size 8 kilobytes, A and B, and then do a bitwise AND of those 2 vectors and store the result in C. And I'm just going to run this in a loop 1,000,000 times, right? The same thing if it was, let's say, 32 megabytes. A vector of size 32 megabytes, another vector of size 32 megabytes, compute bitwise AND and store the result in the 3rd vector, also of size 32 megabytes, and repeat that 1,000,000 times. And what we are measuring is throughput of AND or OR operations. So what do you expect will happen to the throughput as the size increases on the Intel AVX processor?
It should decrease.
It should decrease. Why?
Because as the vector size gets larger, I mean the Intel AVX only has like a certain, probably has like a maximum size for each vector, and
It's two physics bits for each operation. So each time, so with Intel AVX, with each SIMD operation, you can do 2 physics bits. Let's say.
Yeah. So as the size increases, then we have to do more and more operations, and then. Oh, actually no.
We are not comparing the number of operations. We are
right,
comparing
so
the throughput.
Should not change.
It should not change. Constant. You? Constant.
It has to get so many blocks from memory and then
Okay. So what are you saying? First, give me the answer. Is it going to reduce, stay constant, increase?
it should reduce.
It should reduce. Why?
It does so many more memory operations.
But I mean, that's what he initially said. And then the y-axis is not number of operations. The y-axis is number of operations per second. And we are doing it 1,000,000 times. So there are enough operations to be done to at least span a second. Right? I mean, this is the last slide of the lecture. Okay, you guys answer this question and you can leave. I'm pretty sure that's a record, right? 151 right now.
I think it could increase at first and then constant. If a 5 is equal to the cache, then it will go constant.
Did you guys get his answer? Says it. Okay, so to just exactly rephrase what he said, or repeat what he said, he says it will increase and then stay constant, and it will stay constant when it hits the size of the cache. So you said it's constant. You said it's constant as well? Okay. So what do Intel processors have apart from cores? It has caches. It has memory controllers. Okay, it has caches. Okay, how many levels of cache does today's Intel's processor have? What?
3.
3. What do you think is the typical size of the L1 cache?
64.
64 kilobytes. Okay.
That's L1. That's L1. L2 is 256, and L3 is 8 megabytes.
Typical sizes. It doesn't have to be that way. Typical sizes. So typically your L1 is you said 64 kilobytes. That's a very interesting question. Like, but let's not get into that. It may be a different discussion. It's on this system. It was actually 32 kilobytes. L2 is 256. L3 is 8. What's going to happen as we move from left to right on this particular graph? Let's say the size was 8 kilobytes. What's going to happen? I'm running this loop a million times, right? Which cache? So when it's 8 kilobytes, everything is going to be present in the L1 cache, right? If you think about it, the working set of the application, the micro benchmark that we wrote itself, is going to be roughly 3 times the size on the x-axis, right? If the size of each vector is 8 kilobytes, we have 3 vectors that we are running in a loop, right? A, B, and C. So the working set is going to be 3 times 8, 24 kilobytes, which means it's going to fit in the L1 cache. And what happens to throughput if my data is in the L1 cache versus my data is in the L2 cache? Come again? Lower. What happens if it stops fitting in the L2 cache and then goes to L3 cache? It's going to get even lower. What if it stops fitting in any level of cache? It's going to get even lower, right? And that's exactly what we see. This is brilliant, right? On a real system, like getting this kind of a smooth graph, right? And that's exactly what happens, right? When the data fits in the L1 cache, which is only till it is 8 kilobytes, throughput is really high, around 70 gigabytes per second of AND operations, right? And then when it gets to 64, because when it gets to 128, it's not going to fit in the L2 cache, right? Because my L2 cache is only 256 kilobytes. So here it fits, here it doesn't fit, there's a drop. Here it fits in L3, here it doesn't fit, there's a drop. And once you go to memory, it doesn't matter, right? Because now it just depends on the memory bandwidth, right? So that's Intel. That's the Intel AVX. Doesn't have to be Intel. Like any CPU with multi-level caches, you'll see a similar behavior, right? And this is where our mechanism stands, right? We don't expect the throughput of our mechanism to change at all, because it's all happening in DRAM, and there's no cache or anything to play around with, right? So if we assume a single bank here, and this is how much throughput you can get. And as you can see, it's significantly better than getting the data from L2. It is worse than getting the data from L1 with a single bank, right? But how often does your data actually fit in the L1 cache, right? So we thought, this was a really good mechanism. We actually had some evaluations with some real applications. I'm not going to go over those results now, right? But yeah, we have a paper on this. Maybe I can also upload that paper if you guys are interested in reading it. It's just a 4-page paper. Yeah. Cool. So that's it. Those were the 2 goals for the lecture. We wanted to understand how DRAM operates. And in the second part, we want to use that understanding to actually do something more with DRAM. And I hope you guys enjoyed the lecture and understood what was going on. So if you have any more questions, you can ask. Otherwise, we can leave. have a question? No.
Again, when you go to big data sets, can you copy if they're in different subarrays?
Can we copy data if they are in different subarrays?
If it spans the vector span.
Yeah, so yeah. I mean, if you read the paper, we have the mechanisms described there. But so essentially what today's operating systems is, however large your data set is, it's going to divide that into pages. Right? So now a copy operation, let's say that spans multiple megabytes, is probably you're copying one page at a time anyway. So with our mechanism, it'd be, okay, first copy this page. Now if they're within the same subarray, then you can use one mechanism. If they're not within the same subarray, you'll use a different mechanism. So, yeah. Got a question?
Can you explain the mechanism for copying between subarrays, or is that too complicated?
It's actually not very complicated. So, I mean, so if you look at this picture, we have 8 banks. And like I mentioned, we have this internal bus that is shared by all the banks. And it turns out this internal bus is also shared for all reads and writes, right? Because we have only one memory channel going out. We don't have it's a bidirectional bus, right? We don't have one bus for writing and one bus for reading, right? So it's kind of wasteful to have something for reading and writing internally, right? So it turns out internally we have just one bus to both read data and write data. Now let's say I'm copying data from this bank to this bank, right? Today what we are doing is we are reading data from this bank, which puts the data on this bus, goes all the way to the memory controller, maybe all the way to the processor caches. And then at some point we're going to write the data back, which, what happens? Again puts the data on this bus. Now the question is, why not allow this bank to snoop the data when the first time this bank puts it on the bus, right? And not even send the data out of the channel. That's the mechanism. So we introduce a new command which will essentially allow or instruct DRAM to transfer one cache line of data from one bank to another bank using this bus.
I think he's talking about different subarrays in the same bank. Is that right?
Either way.
Okay, sure. I mean, I guess you have that question yourself right now. So let me answer that question, right? So let's say I want to copy data from this subarray to this subarray, right? Now, so one simple mechanism that you can think of is, okay, let's look at what bus is shared between subarrays, right? And that is basically the thick wires that I've been talking about that spans the entire bank, right? You can potentially think of using them to do the copy. But it turns out that reading the data from here to here and then writing it back to a different subarray, now you need to have both rows activated simultaneously. That's not possible in today's DRAM chips, right? For interbank, we can always have one row activated here and one row activated there. But within a bank, that's not possible. So the best mechanism that we could come up with whatever we had was use a temporary bank or a temporary row in a different bank. So if you want to copy data from here to here, first copy data from here to here, and then copy it back from there to the destination.
So
right?
you only have one row buffer per bank. So you can't activate them together.
You have many row buffers per bank, right? This is one row buffer, this is another row buffer. But you cannot activate 2 row buffers simultaneously within a bank today. That's the problem, right? So that's our mechanism. But if you talk to your TA, he has come up with other cool mechanisms to copy data within subarrays of the same bank. Any other questions? Cool. Yep. Thanks, guys. I hope you enjoyed the lecture. If you have any feedback, you can directly email the feedback to me or give it to the TAs, and they can hopefully forward it to me. Thanks a lot.